Uniform continuity. Maybe I'll just refresh our memory about F is uniformly continuous on a set A means it's very similar to the definition of pointwise continuous, but it's a little bit different. For all epsilon greater than 0, there exists delta greater than 0 such that the difference is right here. For all x, y in A, 0 less than x minus y less than delta implies f of x minus f of y less than epsilon. All right, so the uniformness comes in right here where we are saying it's not like we choose C to begin with and then let x be anything else. We choose both points, x and y. Y is playing the role of C. We let both points be anything, and then this has to be true. The same usual conclusion from continuity. All right? Uniformly continuous on a set. The way to think about this, like from on an intuitive level, is basically uniform continuity means sort of that the slopes are bounded, that the slope doesn't like increase forever somehow at any point inside A. All right. And the other thing that you have to remember is to show that something is not uniformly continuous. F is not uniformly continuous. The typical way to do this would be using sequences. F is not uniformly continuous on A if we can find sequences xn and yn, both of which are always in A, with xn minus yn approaching 0, but f of xn minus f of yn not approaching 0. All right? So you have to invent two sequences, which it's kind of like those two sequences are approaching each other. That's what this xn minus yn goes to 0 means. It means the distance between the xn's and theyn's becomes 0. But when you plug into the function, those distances, for whatever reason, do not become 0. All right? This is how to show something is not uniformly continuous. So I got one example, and then I got one for you all to try. Are there any, unless there's a question about the definitions? All of this we did last time. That was just the recap. Okay, my example. How about the function is, this is a little weird, f of x equals x squared plus 1 over x. All right. What does that look like? Well, it looks kind of like the parabola. I mean, I don't know how helpful this is. This is x squared, right? And then 1 over x is this, right? Everybody knows that. When you add them up, what does it look like? Well, I'll show you. It looks something like this. This is kind of strange, but that's what it looks like. What you see here is basically like, this is like the original parabola, only when you add this to it, it usually doesn't matter because over here the values are close to 0. But in the middle, what you're adding on gives you an asymptote here and also here. So that's how you should think of this. I don't know if it even matters. That's what the graph looks like. All right, however you like to think about it. Okay. And I would like, I have two different domains, one on which it is uniformly continuous and one on which it is not uniformly continuous. But when I look at the picture here, basically it is uniformly continuous on domains where the function does not just go up forever or down forever. It will be uniformly continuous on sets which don't include those upsy downsies forever things. But it will not be uniformly continuous if your set does include a region where it's going up forever. So let's first show this is not uniformly continuous on, for instance, the open interval 0 to 2. That's something like here to here. There's nothing really special about 2. The important part of this is the 0, right? It's not uniformly continuous on this interval because on the left side of this interval the function is going up forever. And that's where the uniform continuity breaks down. All right? Even though it is pointwise continuous on this domain, because I excluded the value 0, it is pointwise, like continuous at each point until you get to 0. But if I exclude 0, then it's still continuous point by point, but it's not uniformly continuous. That's the interesting thing. Okay, so for this one, we need two sequences which both approach one another, but when you plug them into the function, it does not approach 0 when you subtract them. All right? And my two sequences must be chosen from this set, both of them. Now, when I look at, you want to have some vague idea of what the picture looks like, just so I can decide what should my sequence be approaching. Like, do I want my sequences to be approaching 2, that's the right endpoint, or should they approach 0, which is the left endpoint? In this example, I want them to approach 0 because this thing here where it's going up forever, that's the whole reason why it's not uniformly continuous. So actually the 2 is pretty irrelevant here. I'm going to choose my two sequences to be two sequences which approach 0. Both of them approach 0. But when I plug it into the function, somehow I need to choose my sequences so that this does not approach 0. But we'll think about that later once we get there. So anyway, I'm going to choose, I'll try and write down my reasoning here. I will choose xn and yn, both converging to 0, since near 0 is where the sort of the weirdness happens in this function, right? There's a vertical asymptote there, and that vertical asymptote is the reason why it's not uniformly continuous. And so that's where I want to focus my sequences on. They should approach that vertical asymptote. Two different sequences which approach 0. The first one's easy to think of. I think you all know what I'm thinking of. Your favorite sequence which approaches 0 should be 1 over n, right? So I'm going to let xn equal 1 over n. What's my second favorite sequence which approaches 0? Unfortunately, I can't use my second favorite, just between you and me, is negative 1 over n. I like that one too. But actually, that's not appropriate in this problem because my sequence has to be taken from this domain, and negative 1 over n is over here. So you can't use that. I have to choose another sequence which approaches 0. And this, when you're doing these kinds of arguments, it's a bit of a trial and error, or sort of, you have to kind of get accustomed to how these arguments generally work out. So I'm going to give you some options here. I'll tell you the one that actually works out. But for yn, I would try, so variations on 1 over n. It can't be the same sequence, but it has to be something which is kind of close. I would suggest you could try something like 2 over n. That sometimes works. Or you could try something like 1 over n squared. Sometimes that will work. Or you could try something like 1 over n plus 1. These are all of my big ideas. So if I were trying to do a problem like this, I would try one of those and just see what happens when you plug that in for yn. Now, I worked this one out ahead of time. I happen to know that which one did I do? Yeah, this one ends up working. Actually, the other ones might also work, but I happen to know that 1 over n plus 1 is going to work in this case. What you need is just two variations on this, basically two different sequences which approach 0. It has to all work out nicely when you plug into the original function and subtract like this, which is hard to predict which of those options is going to work out. I would say just try them out. All right. So anyway, let's decide. So I'm going to do yn equals 1 over n plus 1. All right. So what we need to verify is, first of all, absolute value xn minus yn. Remember, what we have to show is that this goes to 0, but when you plug it into the f, it does not go to 0. So this, plugging into the no, I was going to say plug into the function, but you don't. This is just xn minus yn. So I just use these guys. Absolute value 1 over n minus 1 over n plus 1. Now you could try to simplify here with the common denominator or whatever, but you don't really need to. I'm trying to say, what is that? Can anybody say what's the limit of that when n goes to infinity? It is 0. This, you know, if you remember you're just doing simple limits from calculus, 1 over n goes to 0. 1 over n plus 1 also goes to 0. So this goes to 0 minus 0, which is 0. So this goes to 0. Each of those fractions, when the n goes to infinity, the fractions go to 0 because the n's on the bottom. Okay, that's good, right? We need this to go to 0. The next part is the more interesting part. We need f of xn minus f of yn to not go to 0. And this is the part which may or may not work out depending on, you know, which of these various options or variations on the y's you choose. All right, so f of xn, f of yn. This would be, let me just say, first of all, f of 1 over n minus f of 1 over n plus 1, right? I just plugged in xn is 1 over n, yn is 1 over n plus 1. Now you plug these guys into the original function, which was x squared plus 1 over x. So, I'll be a little careful here. F of 1 over n will be 1 over n squared plus 1 over n, right? I'm plugging into f of x. Is that clear the way I wrote that? Maybe I should. It's this. Plugging in x equals 1 over n to x squared plus 1 over x. Looks like that. And then I plug in 1 over n plus 1 to the same thing. So minus, and now 1 over n plus 1 squared plus 1 over n plus 1. Right? And now simplify. Did I do that right? I think so. Somebody had an unsure look on their faces. That's all right. Okay, now let's try and simplify if we can. This 1 over n, this is 1 over n squared. I'm not going to try to simplify too hard. This is n, right? 1 over n. Minus, okay, this, I'm just going to leave this one. 1 over n plus 1 squared plus n plus 1, right? But actually, it should be minus, because I distribute the minus. Whoa, sorry. Minus n minus 1. I think that's how it goes. All right? Leave those fractions like they are. You will see the n's cancel. I got a plus n and a minus n. And then I have a minus 1, which doesn't cancel anything. So this is, those cancel. I end up with 1 over n squared minus 1 over n plus 1 squared minus 1. And I think this is simple enough that I can just take the limit now. Anybody say, what do you get when you take the limit in n of that? Yeah? Yeah, -1 inside the absolute values, right? Those fractions each go to 0 because I'm taking n to infinity. So this is like, this goes to 0, this goes to 0. I end up with absolute value minus 1, which is 1, which I will remind you is not 0. So this thing, sorry, I should have said equal. This equal sign is really a 2, the limit, right? The limit of that is 1. It is not 0. This is what we wanted. So f of xn minus f of yn is not, no, does not approach 0. That's what we wanted. All right. There's a bit of work here, but it's mostly fairly simple, kind of simplifying stuff, right? The real task is kind of to choose these sequences properly, the one and the other. Now, I did 1 over n and 1 over n plus 1, although if you had used either of these, actually I don't know, these other ones might, maybe they all work in this problem, or I don't know, I didn't try all of them. I just tried that one. All right. Great. So that was the first part I wanted to do. It is not uniformly continuous on this domain. That's how you show something is not uniformly continuous. Let's show that it is uniformly continuous on some other domain. Now, on which domains will it be uniformly continuous? Basically, domains which avoid this vertical asymptote, and also domains that don't stretch out forever this way. Because if I took the interval, say 3 to infinity, that's too much also, because this is kind of like a vertical asymptote if you're going all the way out to infinity. All right, so just avoid that. So let's show it is uniformly continuous on, I had decided to do the closed interval 2 to 5. There's nothing actually really special about the 2 and the 5. It's just that you have to avoid, like I said, you have to avoid that vertical asymptote, and you also have to avoid trying to go all the way out to infinity. All right, let's see if we can prove this. So this one is a little bit more formulaic, although this one also has some tricky steps in the middle. So, but anyway, I will say let epsilon greater than 0 be given. We'll find delta greater than 0 such that for all x, y in the interval 2 to 5, 0 less than x minus y less than delta implies f of x minus f of y less than epsilon. All right, this is the setup. And remember, x and y are between 2 and 5, and this will be important. We're going to use that fact as part of the proof, as in our inequalities. That is going to have to come up. All right, let's do our sort of red section here, simplifying f of x minus f of y. And our goal here will be to somehow factor out x minus y from that. So plugging in, first of all, f of x, remember, means x squared plus 1 over x, minus f of y is y squared plus 1 over y. All right. And we want to somehow factor x minus y out of that. Anybody have any big ideas here? There are some sort of instinctive things I would do here, even without having any big picture in mind. Yeah?
You could first distribute the negative.
Yeah. Distribute the negative is a good idea. And then did you have another idea?
And then you could you rearrange it so the x squared and y squared are the same?
Yeah, even without knowing where this is going exactly, I still feel like putting the squareds together and the 1/overs together. I don't know, that feels like a good idea to me. Now is when you have to actually kind of start thinking a little bit about this. Although my plan would involve looking at these two parts separately, right? Here and here, because for instance, x squared minus y squared, actually I do feel like I could factor x minus y out of that, right? That's the old difference of two squares thing. So I'm gonna try to handle this one, the x squared minus y squared, as totally separate from the other one, and a good way to do that is I'm gonna do the triangle inequality right here to split it like so that now I really can just totally separately consider those two parts as if they were just two totally different things. That's the triangle inequality. When you split up a big sum inside of absolute values, you split it up into the sums of smaller absolute value parts. All right. And now the first half of that, the first one is fairly clear, I think, how to pull x minus y out of that. So I turn the first one into x minus y, x plus y. And then I guess in my next step, you mind me writing half steps here, I'm going to do that, right? But what about the rest of it? So here, anybody have a suggestion about 1 over x minus 1 over y? Can I make 1 over x minus y and then factor that out? No, that's not how you add fractions. 1 over x minus 1 over y is not the same as 1 over x minus y. How do you add fractions? I would say you should do the common denominator thing. I don't know if this looks like it's going anywhere, but actually it is going somewhere. Do the common denominator thing here. The common denominator should be x times y. So this one will look like, I believe, y minus x on top over xy, right? The first fraction I have to multiply by y, and the second fraction I have to multiply by x. Okay. What about that thing then? This fraction here, can you factor x minus y out of that in absolute value? It's got a y minus x. How do you get like an x minus y out of that? Yeah, since it's inside the absolute value, actually y minus x is the same as x minus y, because the one is the opposite of the other in sign. So this actually you can straight up factor out x minus y. That's the numerator, and then what remains is this. All right? Okay. This is more simplifying than we typically would have to do in the middle of one of these things, but that's all right. We can handle it. Our goal is to factor x minus y out of everything, and actually you can do that at that point, because I have two things added together and they each have an x minus y. So this really is x minus y all by itself times all this leftover stuff. X plus y plus 1 over absolute value xy, like that, all right? And now, the typical thing which we would do is somehow say that this part is bounded. Is this part like less than 10 or something? And then I can say the whole thing, I'd say like let delta be epsilon over 10 or something. Like whatever this is bounded by. And I think this part actually is bounded because I scrolled past it, but because of this, right? X and y have to be between 2 and 5. That's a 5 right there. It's an ugly looking 5. So what I'm going to do here, this is the last step of this big old simplifying thing. I'm going to say less than or equal, and I'm going to replace those x's and y's with whatever is like as big as possible, right? So when I see x plus y here, I'm going to make those 5s. Because whatever this is, it has to be less than, if that was, 5 plus 5. That's as big as that part could possibly be. And what about the next part? How big would that be? Actually, if you plug in 5s for the x and y there, that would be the smallest, because they're in the denominator, right? The biggest possible thing, the second one would be, is if I plug in, did I say 2? Yeah. 2 is the lower side of that interval. I can predict your question. Are you really allowed to plug different values in the two different places? Was that your question?
Yeah.
Yeah, this is a little strange. Are you really allowed to plug two different values? Over here, I said this is going to be the biggest one, x and y are both 5. And I said this fraction is going to be the biggest one, x and y are both 2. Anybody feel awkward about that? I mean, it is a little awkward. Do you have an answer to your own question?
I was thinking, is it because like we have an inequality, we're making the whole thing bigger?
Yeah, right. So it is a fact, actually, this stuff can never actually be that big, because the x has to be whatever, like this x has to be whatever that x is. But I don't really care about that. All I care about is, in theory, like what is an upper bound for this thing? And that number is an upper bound for this thing. This would be 10 plus a fourth. Would you mind if I just say this is times 11, right? I did another inequality. It was 10 plus a fourth, but I don't care about that. I would rather just write 11 there. It's less than or equal to 11, right? Now that stuff in the parentheses, like at the top there, that stuff never actually equals 11. It's always less than 11, but that doesn't matter. I just want something which is always bigger. And 11 certainly is always bigger, all right? And this is the end of that simplifying business. Now so this was a little tricky. It involves sort of a lot of simple inequality type tricks, all right? But anyway, I am ready to conclude the proof, all right? I say what do I choose for the delta? Epsilon over 11, right? Then if x minus y less than delta, we have f of x minus f of y is x squared plus 1 over x minus y squared plus 1 over y. Skipping many, many steps, this is less than or equal to x minus y times 11. And that is less than epsilon over 11 times 11, which is epsilon. That's that. All right. I would say this is kind of a hard example. It took half the class to do this example. Remember I said I'll start off with a quick one and then I'll have you guys do one. That took 27 minutes. But the one I'm going to ask you to do is not this complicated, but I'm trying to give you show you all the stuff that could happen so that when you encounter this kind of thing on the playground, you will be prepared. Yes?
So, like, is it generally through, like, your strategy? Like, when you get to that part where you have to pick up, you're always picking the biggest values.
Yeah, right.
That make it the biggest.
Yep. Yeah, because I'm using this less than or equal.
And then if we get an awkward number, should we just, like, go on with it?
If you want. I mean, it's not really necessary. I could have left this as 10.25 and then say let delta equal epsilon over 10.25. I don't like the decimals. I don't know. Yeah. I mean, at this point you could have said, oh, let's round it up to 100 just so that because I don't like 11. Whatever. It doesn't matter. You can do whatever you like. Actually, there's I don't know, no, you probably didn't hear. There was like a major unsolved problem in number theory was just proved, or at least there was some major advance towards it by this guy named Yitang Zhang, who's a big deal in number theory these days. Yitang Zhang proved a major theorem about prime numbers about 10 years ago, while he was at the time that he proved this theorem, he was a substitute teacher at UNH, the University of New Hampshire. He was not tenured, or he wasn't a real professor. He would teach a course here and there every so often. He proved this major theorem, and he immediately became famous. And now he's, I think now he's at Princeton or something like that, as some big school immediately gave him tenure, from nowhere. But he's older than me, and he worked at UNH. He was actually the manager of a Subway, the sandwich shop. He just, for whatever reason, I think he went to Princeton as an undergrad or for grad school, and everybody thought that he was great, but for some reason he couldn't get a job. I think he doesn't speak English very well, but he wanted to live in the U.S., and it's hard to get a teaching job. But anyway, he's now regarded as a superstar, even though he lived for 20 years in total obscurity. But anyway, he just I was just reminded of this because he just proved another major theorem, and part of his argument, it wasn't in analysis, but he was doing some kind of epsilon type stuff, and he rounded up one of his upper bounds to 2022, just because that he was this is a big year for me, so he decided to just sort of artificially inserted that number into his proof, just for fun. It was an upper bound, so it doesn't matter. You can put whatever you want. Okay, that's a fun story. Let's do an example. I got one for you to try. So this is a somewhat simpler than that. How about f of x equals 1 over x minus 3? All right, and I would like you to find a set on which it isn't uniformly continuous and prove it. So you choose the set on which it isn't uniformly continuous and prove it. And then, same thing, but find a set where it is uniformly continuous. This one should be similar to the one I just did, although all the simplification stuff is much easier in this example. Find a set on which it is uniformly continuous. All right, I'm gonna walk around and see how you're doing once you get going a little bit.
We might break it, and that might be on the top. One ring plus 3. One ring plus 3. Plus 3. All right.
Divided by 4.
Yeah, okay.
This is 1. Okay, this equals -1.
Yeah.
What is this again?
That might just be a small variety. So we'll go to
Oh, the little double bracket.
I looked up what the double brackets meant, and the first thing that came
they'll both
up
go to
was
30.
the video that what is it? I talked about how we need it.
We don't want that.
No, we want that.
Oh, yeah, we want those to convert. We want the other ones to go apart, so we actually check the function.
So now we need f of xn minus y
This part goes to
which is 3 plus 1 over x minus 3
Joe, you want the difference in zero and numbers. So I don't know.
No. Well,
I'm gonna say this goes
you want to see.
Three and
subtract the 3.
yeah, okay. I don't know.
Because
It gets-
Goes to the end, one round, one
That's good. an approach 3.
Because it's still a good choice for me.
Yeah.
But all the numbers are like say approach 3.
Oh,
we have to use that last
and that's not
Yeah, they have to
really
be
right.
both on the same side.
How far you get? No. You have to do zero.
Alright,
So you didn't actually plug it in. How do we know it doesn't go
so any comment? What's your step?
We did the last all tomorrow.
We found that it goes to zero.
You can't really use R because that's
No,
not,
like the function goes to 0, so you can take 3.
that's
No, that's
larger
like
than
the distance between the two sequences.
But 3 is excluded from going.
We need
So
to-
whatever set you choose has to be.
We need the distance.
Oh, I wrote it wrong.
Doing alright?
I thought we were doing the.
This is a good choice.
Yeah.
Yeah, this is a good choice too. Yeah. Try something for the other one.
Yes, x and y goes to 0.
Yeah. Now we need the other.
Yeah, there we go. There we go. Typo there. Typo in my Python, which doesn't make any sense. Spelling mistake.
Anywhere?
We're plugging that into that. So.
Oh, right. God. Honestly, it's not super fun.
You were talking to me about this earlier.
Oh,
I remember you telling me
It's
about
just a lot of steps.
Yeah.
Well, you got it. Yeah, so you have
Anywhere?
I think just that.
1 over 3 plus 1 over minus 3. Oh no, this converges to 0.
No, it goes to. 3 minus 2 is that, and 1 over n equals n, and I then
Oh, so I use both of them.
all of them then goes to 0.
Oh, right. So we have
Yeah, red one. So it doesn't really.
this is that's right n minus
So it just goes to
n minus n plus 3. And then this is that's by negative 3, which is 3. So
This worked out?
thing,
Yeah,
which is 3. Okay. Which is left great. 0.
No, it's supposed to. How do you get 3?
The absolute value.
Yeah.
Wait, wasn't it supposed to not go to 3?
Wait and see.
Wait, it actually went to 3.
No, that's fine.
We should just show that they go to different places.
Well, yeah, this one must go to 0.
Yep.
And this one
Must not go
does
to
not go. Doesn't. Goes to 3. Because these are like, what those sequences are, they're supposed to be like infinitely
This
close
is
together.
that's because the theorem with the sequence is it's like when you have your sequence function that sequence goes to.
Yeah, 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 yeah. So you would, if, in a true and just world, this really ought to be 0.
Okay. Well, we would go first sequences, right? What's the second part? Do one where it is. Is it here? So we took pick on the there's no asymptote. Well, let's see. 3 is the asymptote. 5 is asymptote. This is good. You're supposed to watch this. Is this on? These problems.
Well, actually,
There's a lot of this takes so much time. Actually, twice it doesn't really make really. But I suppose if I don't do it right after this class, I won't learn which number yet. That's a definitive thing. Okay.
I know not everybody's done yet, but I wanted to talk about these before we leave today. So let's go over this. Most people are just getting through with the not uniformly continuous part, and it looks like everybody ended up making it happen. The way I did this, which is I think probably different from everybody else, I wrote it is not uniformly continuous on. Actually, can we do the one where it is? Just because as I'm walking around, I think most people are working on the is uniformly continuous part. Anyone want to give me a set where you were trying to do this? I know not everybody's finished, but it should be some set which avoids the asymptote.
5 to 7.
5 to 7, okay. This should work. It really doesn't matter much. In fact, in this example, you could even go 5 all the way to infinity, because in this function, as it goes out to infinity, it levels off, right? But anyway, 5 to 7, great. This one, so would you mind if I just write sort of the middle part of the proof, just because we have to go in a few minutes? It involves this, f of x minus f of y, right? And this I say, just plugging in, I get 1 over x minus 3 minus 1 over y minus 3. And my goal is to somehow factor out a x minus y from that. What did you do with this? Did anybody? Even if you're using a different set. Yeah, do the common denominator and subtract the fractions here. So the first fraction I have to multiply by y minus 3. And then the second fraction I have to multiply by x minus 3. I don't think it's helpful to do the distributing in the denominator, but this is what you get when you subtract. And then if I combine the stuff up top, the 3's will cancel. And then I end up with y minus x, which I can turn into x minus y because it's inside the absolute value. So this, skipping a few intermediate steps, looks like this. All right. So regardless of which domain you chose, you should have done these same steps. Now it matters which domain you picked, but what can we do with this? When I look at this, I like x minus y. I'm going to leave that like it is. This part I'm going to replace with an upper bound. And you just have to decide. I mean, when you have an interval like this, generally your upper bound, your choice is basically, should I use the 5 or the 7 for the x and the y? And this will depend on if it's in the denominator or in the numerator, or perhaps if it has a minus sign in front of it or something. What do you think? Should I use the 5 or the 7? The 5, yeah. In this case, I want to make the fraction as big as possible, which means I want to make the denominator as small as possible, which means I should use the 5 for both x and y. So this is going to be 1 over 5 minus 2 times 5 minus 2, like that. Those are 3's each, I guess. So this is less than or equal to, well, at this point, it's equal to x minus y times 1/9. All right. If you chose a different domain, you would get a different. Should be 5 minus 3. Yeah, thanks. I somehow did 2 steps in my head when I should have done 1. Okay, so then it's not 9, it's 4. All right. And so from here, I would finish by saying let delta be, I guess, 4 times epsilon, etc. All right. If you used a different set, you would have plugged in a different number here, but you would have plugged in whatever the lower limit of your set was. Yeah.
I got there and I just said that means it's less than or equal to like x minus y. Is that okay?
Sure. Yeah. If you don't like this fraction here, you could like round it up to 1,000 or 1 in your case. Yeah, that's more reasonable than 1,000. Yeah. You could, if you like. If you want to simplify things, you can just say this is less than or equal to that, and then you would just use epsilon rather than 4 epsilon down there. Yeah, great. We got 4 minutes. Is that enough to write just a few bits of the other one where it is not uniformly continuous? I saw lots of people having good luck with, let's use the set not uniformly continuous on, let's do, say, 3 to 5, I don't know. It should be a set, an open set which has 3 as one of its endpoints. So you want the set to be approaching 3 but not actually include 3. And then I need to choose 2 sequences which both approach 3, and they have to be taken from inside this set. So I'm going to say let xn be, how about 3 plus 1 over n? Those numbers are a little bit more than 3. And then for the other one, actually, if you looked at my sort of 3 alternatives, I think all 3 of them will work. Any of those choices would have worked in this particular example. Maybe I will choose 3 plus 2 over n, just because I think that might be algebraically the easiest way to do it. All right, and so next I would verify, first of all, xn minus yn in absolute value. This is 3 plus 1 over n minus 3 plus 2 over n. The 3's cancel, and I just end up with 1 over n minus 2 over n. That is negative 1 over n, I guess. Anyway, this goes to 0, right? So that's the first thing you need. And then you check, and this is the part that you are never quite sure is going to work out until you try it. If I have a very complicated function, actually, I find it would be helpful to use a computer to do all the simplifications for you. You can do that if you want to, although not on our test, or it's not terribly useful for a class such as this. But in real life, I would use a computer to do all this simplifying. What? I've forgotten my function. 1 over x minus 3. Okay, so this is 1 over n minus 3 minus 1 over 2 over n minus 3. All right? This is kind of an ugly thing to have to simplify, but did I do that right? 3 plus, yeah, thank you. Then it's not so bad to simplify. Yeah, it's 1 over, yeah, 3 plus 1 over n minus 3, right? That's how it is. And this one, 3 plus 2 over n minus 3. All right, this, the 3's all cancel. I get 1 over n, which is just n, and then minus 1 over 2 over n, which is n over 2. This is just n over 2, and that does not go to 0. This, in fact, is unbounded, right? This goes to infinity, but it doesn't really matter what it does go to. All that matters is it does not go to 0. All right. Great. And that will do it for today, I guess. Better be one of these on the test, am I right? This was like a whole day on one example, but I'm glad to do it. All right, we do have our test a week from today. So as I said before, we're going to do new stuff on Monday. Will not be on the test. Wednesday, we'll just do review for the test, and then we'll do the test. There will be a homework due on Wednesday, and I'm really going to make the assignment today.